Okay, so in this video, I'm going to go over the solution technique for perfect complements now that we know how to identify them with that min function. And then I'll do a quick example with actual numbers, then drawing an angle curve for these perfect complements. All right, so remember, like, the problem that we face is to max the utility function, whatever that looks like. Here, it's like, some min function. Let's do the simplest one, subject to some budget constraint, right? P1 x1 plus P2 x2 equals M, and the consumer gets to pick how much of each of the goods they want. Now, with these min functions, if we draw out the problem, we have these right angles for the indifference curves. This is like I0, this is like I1. And then we have like this straight line for the budget constraint, right? The slope of the budget constraint is negative P1 over P2. And so we have this straight line for a budget constraint, wherever we want to put this budget constraint. And so the solution graphically is going to be where this budget constraint hits one of these king points of these indifference curves, right? And there's like an infinite number of these indifference curves. So there's going to be one that it just touches this point here. And this is the solution to this problem, x1 star, x2 star. The issue here is that we can't use, we've learned these different techniques to solve it, and the big one that we've kind of covered a lot is this tangency condition, where the slope of the indifference curve is the slope of the budget constraint, right? But that's not happening here because of this right angle, right? Like it's not tangent, like the tangency doesn't exist. So like we need to figure out a way to how to identify this point here. We can call it like point A or something. And how we do that is basically we know that the optimal point is going to be at one of these like little right angles, these kinks of the indifference curves, right? Didn't draw them that great, so it's going to be somewhere along this line that passes through all these kinks. And the slope of this line is where these two arguments are equal. Or maybe I shouldn't say the slope of the line, but that line is where these two arguments, whatever they are equal. So this line is x2 equals x1 with this example here. I don't know why I did it the other way, but if we had another one that was min x1, 3x2, this line that went through all the kinks would be where x1 equals 3x2 or x2 equals 1/3 x1, right? So like that would be the equivalent of this line with these preferences for this utility function. So that's like one thing that we know must be true. We must be consuming along this line because that's the line that passed through the kinks, and we're definitely going to be consuming at these kink points. Otherwise, we're wasting our money with these perfect complements, right? We're buying too much of good 2 up here. It's not giving us any utility. We're just wasting our money. So we're definitely going to be consuming along one of these kind of right angle points. So that's one equation we know. So the first equation is the line that passes through all the kinks. So for example, here it was where x2 equals x1, but it's going to depend on whatever our utility function is. But it's really just setting those two things equal to each other, and that's how you can see where the kinks are, and you can express it as x2 as a function of x1 if you want to think of like a line. Okay, the other thing we know is that we're going to be spending our whole budget. These are goods, so we're going to be spending our whole budget, and so we're somewhere along this line here. The other thing we know is our budget constraint. So here are two equations, and we have two unknowns. So we could solve for this, right? The two equations are these two things here, these two equations here, the budget constraint, the line that passes through the kinks. And the two unknowns that we're solving for are x1 star and x2 star. So this is how we're going to solve these perfect complements. We're going to identify them by using the min function. Then we're going to think about what's the line that passes through all these right angle points where these two arguments up here are equal. That's that line. And we also know we're spending our whole budget constraint. That's going to give us two equations and two unknowns, and we can just solve for x1 and x2 star. So let's do an example with like numbers, and hopefully that will help. So here's an example that we did in class, in my class of Queens. So Emma always liked to drink tea and eat donuts in fixed proportion. There's that key word that we know right away that we have perfect complements. In particular, she always has half a donut with each tea she drinks. Having more than half a donut with her tea or having more than one tea per half donut doesn't increase her utility. This is the question telling you it's perfect complements without just giving you the utility function. Then it gives information about the budget line. So she has a weekly budget of 20 bucks. That's what M is equal to. The cost of a donut is 50 cents and the cost of a tea is $1. How much tea should she buy? How many donuts? So this is asking you what's x1 star, what's x2 star, whatever you want to label the tea and the donuts. And I ask you to draw a diagram of your solution. All right, so the problem here is to max her utility, and her utility is this min function. If you look at the question, we got to talk about what it is. I screwed this up in class, so let's make sure it's right. That she's always going to have twice as much tea as donuts, right? The number of donuts she needs is half the amount of the number of teas she needs, because she only has half a donut per tea. So this is going to be true at the optimal point, right? Like the amount of donuts is the amount of tea. She's always going to have half the amount of donuts that she does tea. Hopefully you can intuitively kind of see that. You know, you could express this in different ways. It could be T equals 2 times the number of donuts. She needs twice as many donuts as tea. Sorry, she needs twice as much tea than donuts. Either way works. It doesn't matter, right? These are just monotonic. I mean, this is just rearranging it, but you could also like multiply by 5 or do whatever you want to it. Okay, so I'm going to say this. You could do it whatever order. I don't think I even say in the question which order you should do it in or which good is which. So there's our utility function. She's picking the amount of donuts and the amount of tea she wants. And we've got to write out our budget constraint. So each donut costs 50 cents, so it's 0.5D plus 1 times T equals 20, because the price of tea is 1, the price of donuts is 50 cents, and she has a budget of 20 bucks. So this is her problem, right? Like we basically outlined her problem here. Now we know that it's a min function, so we got to use this technique to solve it like we just talked about. We have 2 equations and 2 unknowns. We know optimally this is going to be true, and we know she's spending our whole budget. Right, if you want to draw a graph of this, which I guess the question is going to ask us to do anyway, I think donuts is good 1 with how we did it. Tea is good 2. We know that we have these right angles where D equals 1/2 of T. So these right angles, like indifference curves, whatever they look like. Hoping to draw them with some straight line, but as we know from my class, none of my graphs are really to scale, but this line is t equals 2 times d. I'm just doing it like that because t is on the y-axis, and I always think about graphs as being like y equals something, right? All right, so this is what we're trying to solve for. There's our diagram. We just got to add the budget constraint in a minute. So if she spends all of her money on donuts, she could get 40 of them. If she spends all of her money on tea, she could get 20 of them. So those are our two axes. We can just pick whichever indifference curve we want to be the solution. It's this one. I'll do the budget line in red. So this is 20 if she spends all of her budget on tea, and 40 if she spends all of her budget on donuts. Or this is like 20 over 1, m over p1 or p2. And this is m over p1, which is 20 over 0.5. And we can see the slope is, remember, negative p1 over p2, which is just negative 1/2. p1 is 0.5, p2 is 1, so the slope is 1/2. So this is like the solution that we're trying to find, this t star in d star. And we're going to use these two equations and two unknowns to solve for it. And we'll just put the numbers on once we solve for it. Okay. All we have to do, and I'm guessing I'm missing a D here. All we have to do is plug this into our budget constraint, right? Plug this equation into our budget constraint. So I can rearrange that and say t equals 2 times d. Like working with these whole numbers rather than these fractions. So we have 0.5d plus 2d equals 20. 2.5d equals 20. D equals 20 over 2.5, which equals 8, I believe. So d star equals 8, which means t star is equal to 2 times the amount of donuts. Remember, we always need twice the amount of tea than donuts, is 16. So 16 and 8. So solution technique, figure out the line that passes through all the kink points where these two terms are equal. That's one of the equations where we know that the optimal solution is going to be on. The other one is we're spending our whole budget. Use those two equations and two unknowns to solve for these optimal amounts. We just did an example. We're given kind of a general description of Emma's preferences and her budget. Here in Max, we figured out that she always needs twice as much tea as donuts. That determined what our utility function looked like. Here's the budget constraint with the prices. We had two equations and two unknowns. One was the line that passes through all these kink points. At that point, it's t equals 2d or d equals 1/2 of t. And the second equation is just that budget constraint where we got to remember to put the d in there. We have those two equations and two unknowns. Plug the first equation into the second, solve for d star, or you can do it, solve for t star first, whichever one, and then you plug it back in and find the other good. So we figured out that ultimately she's going to buy 8 donuts and 16 teas, and that's going to maximize her utility. All right, the next question is about this angle curve for t in this case. Remember, this angle curve is relating income to x. Well, I guess I should write it as t. So m and t. It's relating the amount of t you want as a function of income kind of thing. Okay, so we got to go back a little bit here and make sure we kind of have to resolve this problem, but instead of having a 20 here, we leave income as m. And we kind of just resolve this problem, and we can get like t star as a function of m. Here we just got like an actual number because we have prices and an income. If we leave m as like a general m instead of a 20, we're going to find t star as a function of m, and then we can plot that curve, if that makes sense. Okay, so basically the problem is max, I don't remember what we said the utility function is, d and 1/2 t. We get to pick the amount of d and t, subject to 0.5 d plus t equals m. So I'm just leaving this as m here rather than plugging in the 20, just because I want to be able to draw this angle curve. Okay, again, two equations, two unknowns. First equation is that d equals 1/2 of t. And the second equation is 0.5 d plus t equals m. We can plug 1 into 2. And so we get 0.5 times 0.5 t plus t equals m. Say 1/2 is 0.5, and I'm just plugging that in. So we have 1.25 t equals m. And here's like an equation where m is a function of t, which is really convenient for drawing a line, right? We say it's a straight line with a constant slope of 1.25. So there's our angle curve. All right, so hopefully that helps you when you have to tackle these problems that are perfect complements.